Okay, so now that we know what a power series is, one way that we can think of it is a function of x, and it is so functions have domain, and the domain of our power series is going to be all of the x values that make the power series converge. We'll see examples of power series that converge on different intervals, but one thing we should know about any power series is that they will always converge at their center. And the reason they will converge at their center is because if I look, let's take this general expression for a power series that is centered at C. So if I want to see what is happening to this function when x is C, I now have the sum from n is equal to 0 to infinity of a sub n c minus c. I've plugged in c for x to the nth power. Well, that's just the sum of 0, which is equal to 0, and that's definitely converging. That's just a single number. So a power series is always going to definitely converge at C. C will always be in the domain of a power series. The next theorem that we're going to look at shows us that the domain of a power series can have one of three forms. It can have what we just talked about. It only converges, it converges at C, its center, and it only converges at C. Another option is that it could converge not just at the center C, but also in some interval around the center C. It could also be converging there. Later on, we will look at variations of this, or maybe there's a bracket, maybe there's a parenthesis, maybe there's two brackets. We'll explore that. That's where we go into the endpoints of the interval of convergence. And then the other option is that maybe it converges on the entire number line. And that power series converges everywhere. So that's what our next theorem says. So we've seen three illustrations of that, only at a single point C in the center. Number two, where it says there's some real number R such that the series converges absolutely for the absolute value of x minus c being less than r and diverges for greater than r. All that means is that it's only converging on this blue interval right here, and that it would be diverging on the outside of that. And then number three, the last option, is that the series converges for all x. The number r is called the radius of convergence. And r is the length of that interval that, half the length of the interval that the series is converging on. If the series only converged at the single point C, like that single dot up there, number one in the theorem, then the radius of convergence is equal to 0. If the series converges for all real numbers x, like if the interval is number 3 in the theorem, if it's converging for all x, then the radius of convergence is infinity. And then the set of all values of x for which the power series converges is called the interval of convergence. So that could be an interval that is definitely bounded, like in the second case of the theorem, or it could be an interval that's not bounded, like in the third case of the theorem. Or it could just be one single point, what we see. And now we're going to look at some examples of finding the radius of convergence for some power series.